So we are coming to part 2 of 26 of our course on mathematical methods for signal processing. And I have prepared again some MATLAB demonstration. But before going into this, the live editor is really a nice thing for demonstration. I will learn it myself more and more. I would like to come back to the theoretical part in the following sense, that we have seen a little bit about what a Gabor multiplier is. It's just an operator which, like a Fourier multiplier, multiplies the coefficients. So given a signal, we can compute the Gabor coefficients. We have seen that the samples of the short-term Fourier transform, or maybe more correctly, if we want to have perfect representation, the coefficients of the STFT on a lattice with respect to a dual window gives the minimal norm coefficients with respect to a Gabor system obtained by time shifts by multiple of A, frequency shift by multiples of B, or some other more general lattice in the phase space. And of course, we would like to understand what these Gabor multipliers are, how they look, how you can approximate an operator, and so on. And that's where I'm going back to the script in the sense of, script is, we're changing this by going here, yeah. So one of the questions that can be answered with the knowledge that we have, kind of both experimentally from MATLAB and now with the setting and the mathematical terminology, is how can we approximate an operator by Gabor multiplier? It turns out that the Gabor multiplier is an operator which allows to approximate a slowly varying system quite well. And actually, if you think of a practical situation that the audio engineer is destroying your signal. So maybe he's a rock fan and he wants to boost the deep and the high frequencies and suppressing the middle frequencies. Or the hearing device of your grandfather is emphasizing the middle frequencies so that he can hear your voice better, but it modifies the other ones because they are kind of not important or whatever. And so you see the audio engineer, how he is changing the energy in the frequency channels, and you would like to compensate it because you're saying, this is a classical music, I want to undo it. Then it's very natural to say every amplification with a factor, let's say 2, should be reversed by multiplying with 1/2. So emphasizing and de-emphasizing parts in the time frequency plane can be undone in a way by a corresponding Gabor multiplier with the inverse symbol in the pointwise sense. Now, it turns out that this is a very reasonable approximation, but not a perfect representation. So you cannot undo a Gabor multiplier or even a Fourier multiplier by using a Gabor multiplier, but you can try to do it at your best. So, for example, for low frequency, for nice signals, most of these things work quite well. Okay, so let us discuss a little bit the approximation of a given operator by a Gabor multiplier. So I have to recall the following situation. A Gabor multiplier is an operator, I didn't put it here, but elsewhere, is an operator which takes the Gabor coefficients, multiplies them with numbers mu lambda, and then put it back to the position. So a sum of this form, where I use p lambda for the projection of the atom sitting at the position lambda, which is a point in our time frequency lattice. Now, of course, if you're doing nothing, if you're just taking coefficients, you're multiplying with constant 1 and going back, you would like to have identity. So if m is constant 1, you're just taking the sum over all these atoms. You hope to get back the identity operator, and that's why I'm suggesting you should take a tight Gabor atom. So we were showing you that s to the -1/2 the inverse square root or the square root of the inverse of the frame operator. It's all both is possible. So you could say I have to diagonalize this frame matrix. It's positive definite. It has positive eigenvalues. You take the inverse, but the square root, and then you have a nice matrix applied to your original Gabor atom, and you're getting this such a tight atom, such that if you're adding all the time frequency shifted versions along the lattice lambda, you get identity. Okay, so we want to do this. For example, you would like to get twice the identity if your multiplier is constant twice. Or you would like to say, in this region, I'm emphasizing everything should be doubled. In the other region, everything should be multiplied with 3/4 and so on. So somehow you pave your function with values which are constant. And you would like to know, what can you say about this operator? So actually a simple statement would be, if your multiplication is in the range of 1/2 to 2, so something around 1 in a symmetric way, multiplicatively, then you can prove that with the tightness condition, this operator has eigenvalues, and these eigenvalues are in the range of 1/2 to 2. So kind of question is, where are the eigenvectors concentrated and so on, but we cannot discuss this here in detail. Now, if we are in a Euclidean space and we have seen that the Hilbert-Schmidt operators are having a scalar product and therefore they are allowing to talk about orthogonality, you can say, okay, I have an operator T, which is a Hilbert-Schmidt operators. The finite linear combinations of these are rank 1 operators, so they are definitely Hilbert-Schmidt operators. So if you actually take L2 norm coefficients, you get Hilbert-Schmidt operators. So what among all these possible multipliers, Gabor multipliers, is the best approximation or so? And of course, you can prove in the abstract setting there is a minimal approximation, and this approximation is by taking the linear space generated by this. With the 2 coefficients, you get a closed subspace. So that means essentially these elements are linear independent. So it's like typically kind of 2 n-dimensional space within the big space of our n times n matrices. So it's much bigger space of all matrices. And you're taking a small subspace, but it's always, by Balian law, always larger than n-dimensional. So it's interesting. You can have linear dependent Gabor atoms, let's say 2n Gabor atoms or 720 Gabor atoms, but still the projection matrices are linear independent. Okay, how can we describe this problem? Well, we go to the equivalent problem, and it's really the same number in the Kohn-Nirenberg setting. So we are saying we need sigma of t to be approximated. And the sigma of t has to be approximated by this linear combination of this. Now what we observe is that you have to take m lambda and then you take the sigma of p lambda. But how did we get the projection on Gabor atom at some location? We move the signal back to the original position. We apply the PG, the projection operator of our atom, and then we move it back. But conjugation, that's what I tried to explain last week, goes to translation. So I'm saying, oh yes, we have to, you're giving me the operator. You're asking me, the G of course should be the same as the tight atom here. This would be the projection operator of the tight atom here. You can even take a look in MATLAB then if you want. And then we see that this is something well concentrated, a well concentrated bump function of 2 variables. We're moving along a lattice. That lattice is supposed to be quite decent. So it should not. It should be like, for a Gaussian case, you would have to choose A equal B or so. So you're having bump functions, and then you approximate it. Now the interesting thing is, yes, this can be done quite easily by saying that this is a discrete convolution. You go to the Fourier transform side, and then the Fourier transform of this problem is solved quite easily. So we have code that allows you, given the G tight, or let's say given the G, then the lambda, then we make our window G tight, and we do with this G tight actually, And by starting with the Kohn-Nirenberg symbol of the matrix, we can get this best approximation. And this is a deterministic thing. And then, of course, we can ask the following question: what if we are doing the same procedure that we get and apply it to an operator with a zero kernel? And then, of course, it will be interesting because the G in a zero means the PG is a good operator. It's an operator with a zero kernel. Therefore, Kohn-Nirenberg symbol is in a zero. Therefore, all these shifted elements are a zero. And then, of course, you will not be surprised that you will get L1 coefficients. And that means that that symbol is in S0, and this is in S0 because I have a good operator, so you can measure the difference in S0. But you can even say, no, I might have an operator which is too nasty to be in Hilbert-Schmidt. Well, we'll still have a sigma of t, now in S0 prime. And then, of course, you would have a bounded sequence. It would still make sense, and everything is still, it's not minimal anymore in a particular sense, but it's a procedure which is coming from the Hilbert space situation. So that's the moral also of these rigid Hilbert spaces. You can extend what you have to a much larger domain, but when you know what you should do, start with the Hilbert space setting. So for example, I might do it for next time, still if there's enough time. I might want to approximate, the analog would be, think of this being a kind of a Gauss function, and you would like to approximate a given function in L2 by shifted Gauss functions or so. Well, then, because the Gauss functions are nicely linear independent, if you shift them along a lattice, you would get a certain formula. But then you would say, well, but if my function is not in L2, maybe it's just even L1. And the answer would be, then you would compute in this procedure L1 coefficients. What if it's a bounded function? Well, you would not do the best uniform approximation, but you would use the L2 formula and get something which is still giving you a bounded. And of course, usually the approximation quality for different values of p would not give a completely different one. It's much better to have a uniform formula that you can apply in many situations, which is optimal for the Hilbert space and very reasonable in the general case. Okay, I think I should stop here. I know maybe this, what I've used here is that if you're conjugating an operator with a time frequency shift, so pi is a time frequency shift with pi lambda being, lambda being a pair of time and frequency, and I'm having a first time shift and frequency of the operator, and I can make an operator. I'm saying I make out of my operator T, it's a matrix, I conjugate it with left and right multiplication. The star is the joint, which is the inverse in this case because they are unitary. And the important formula, which I put in blue, is that if you do this funny conjugation, so kind of you make out of an operator which is projection on your Gabor atom, you make a projection on a Gabor atom for a different lattice point. It's just the translation if you take the symbol. So a symbol of this new operator is just take the symbol, the Kohn-Nirenberg symbol of your operator of your matrix and shift it around. So I think that should be enough, at least for now. And I'm jumping back to the MATLAB experiment. And I have the following kind of prepared material. We will go through it and I will show you a few things. First of all, let you look a little bit behind the scenes. I have one file that creates all these variables, and these variables are really just a collection of points in the complex plane. So I'm not sure if it works quickly, but maybe I'm showing you just the size of this object. So S0 is S0, C0, LE is for L1, and I rerun only this first section. So you see this first S0 is the circle, and the circle is just the unit roots of order 2 to the 10, which I'm drawing. So this is the little circle here. C0 is a rectangle, so this is a green rectangle. So I'm more or less saying this is the first point, and I plot with green from here to here to here to here, and I close the circle by having this point at the end again. The same is with L1. So the blue object is L1, the rotated version. So really I'm plotting I times L1, which is multiplication by 90 degree. Multiplication by I is the rotation of the object by 90 degrees or so. And there is this cfill command that allows you to fill with some color, which is magenta, yellow, and so on. So this was just to recall how I'm producing these things. Now the next thing is I wanted to create, to see how I can show it to you. Yeah. I'm creating, with the help of my bupus, and maybe I also should explain those a little bit, a local signal. So, maybe I explain the code first and then run it once more. So I would like to show you that signal plot C XX local. I also want to determine a rectangular filter, and maybe I go down here. The rectangular filter is more or less the indicator set of this red within the red circle. So the kind of things that I'm using here is a function which is localized in time and frequency, and if you change the parameters, you would get a longer signal or more high frequency picture. So I was choosing a fairly narrow picture to demonstrate a different thing. And so the filter would be the constant one inside the red area. So image STF is my command of saying, well, compute the short time Fourier transform, really the continuous, so the n by n matrix. But then I'm doing my lattice points. These lattice points are with A equal 20 and B equals 16. That's my standard setting. Display the A and the B. And the SPI is a SPI which is centered but hold. So I'm not worrying about hold on, SPI, FFT shift off, but I have my private command. And then, because it's a small area, you could look at this. I'm zooming in. And now the interesting thing is, you see here, I have found that 35 points are inside the region. Of course, my filter is roughly speaking 3A to the left and to the right, and 2B in the left and the right. A little bit more, I'm adding a minor margin to this here. Maybe I to have it more symmetric, I put a 2 here, so 3A, and they're enlarged by 2. And then the point is that I'm saying, and before first I explain the text to you. First, we compute the full short time Fourier transform. So the XX local is our local signal, and we compute the short time Fourier transform. But we also find the NDG, the indices which are good, which are just these 35 points from our Gabor family, which are inside the red box and which are also lattice points. So we're getting an index sequence, which is MATLAB indexing of the points, but it's a list of 35 elements. So this is important. We also know that we would recover the signal perfectly by taking the dual Gabor atom. So maybe I should also say we should XX reconstruct is Gab synthesis of STFT with the dual window, of the signal that we want to expand. using the dual window and A and B, and we use the synthesis with this. So of course we have to see, do we really get, that's, I want to convince you that I really, of course, can reconstruct not only from the continuous short-term Fourier transform, but from the sample short-term Fourier transform. But here we would use all these 720 signals or so. Now, going further on here, I would say we compute the full short-time Fourier transform because it's easier to explain what we are thinking, not what we should do for efficient coding. We're saying that the ST short-time Fourier transform of our signal X at the good indices is just taking this full computed at the point. So I'm getting a list of 35 points. And here you have the alternative irregular Gabor routine, which just says, well, let's make a list of 35 row vectors. So we start with the dual. Actually, I should say we could do it. Yeah, maybe. You know, we can change the dual window to the window and to the synthesis with the dual as well. But I'm done. Yeah, maybe. Maybe I'm also doing it this way. I copy it. Gaborek dual. It means we are now analyzing with the window and using the dual window for synthesis. And we also compute this norm. But okay, so what we are doing here is we are saying we have this 0-1 matrix, which contains 35 markers. It's a n by n matrix with 35 ones at the positions of the lattice points inside our red rectangle. And you're seeing here it's a collection of 35 row vectors, which are time frequency shifts of the dual window at those points. And so when we are saying the local approximation, we're just saying, well, take these vectors, and because pulling out is giving a column vector, we make it a row vector, just transposing it, just changing the format, no conjugation. And we're doing this to do linear combinations of our row vectors, so the GD, the local version. Then, of course, we would like to know what is the error that we get. And so I think I can run this session now while I continue to talk. So only at the end, I'm saying we have computed the error. So let's see what we get here. Yeah, so it seems that there's a problem with this first plot. I don't know why. I tried only once, but you see here it's I see. No, that's I see. It's I have to change the figure once more, so I have to say figure. Hopefully it works now. But you see also here, you have seen in between on the right-hand side how small the time frequency area is where everything is covered. So everything is fine. So the full reconstruction from all these sampling points is fine. And so probably this also all these comp norms should be small, and everything is perfect. And we have 35 points. And so this tells you, if you only know for a signal which is concentrated in this area, that you can reconstruct your whole function here. I'm not sure if we can do it, but we can identify an impulse response of a system. So assume now, instead of our function, which we want to analyze by looking at this the short-term Fourier transform or reconstruct from samples, I think we should also explain that it's enough to know the output of a system where this signal is now the convolution kernel, the impulse response, at certain layers. We even don't have to know it perfectly well, but only at lattice points. So we sample an output, we throw in a signal which is concentrated frequency-wise to get all these samples from one kind of series of measurements. We do it for this level, this level. So in our case, we would have only to get, I don't know, 7 measurements for 5 channels. So we're testing this signal, and we try to find out what we can do. And that would be enough to identify the original kernel. Now, here, where is the error? Yeah, here is the non-trivial error. So we are reconstructing from those 35 elements in the domain. And the error is, the signal was a normalized signal. So the error was about, you see the deviation in terms of size is marginal, but the error is about 1% of the norm of the signal. So clearly, of course, you could say, well, what if we would take not 35 elements, which is 5 times 7, but we would enlarge it by 1 row around this, so it would be 7 times 9. So from 63, I would be sure that you get already 1 decimal better approximation or so. And it's the question of the time frequency concentration that you have to do this. Okay, now the next thing I wanted to show to you is the story with the Gabor multipliers. So let me see, yeah, the TFW is a weight function on the time frequency plane. So it's a time frequency weight. So it's a low frequency signal. So it's a smooth function of 2 variables of format n times n with maximal frequency in the horizontal direction of 3 and vertical frequency direction of 5. Okay, what does it mean? Well, we have 2-dimensional pure frequencies, which are plane waves. They're products of 1-dimensional frequencies, and the maximal frequency in the horizontal direction is +3. So I have 0, 1, 2, 3. I have also -1, -2, -3. So I have 7 possible frequencies in the time direction, and I have 11 frequencies, pure frequencies in the vertical direction, which means if I take all the pairs, I have 7 times 11, which is 77 plane waves. So this signal is constituted as a random linear combination normalized so that the Frobenius norm is 1 of 77 random pure low frequencies. So somewhere you should see that the Frobenius norm is 1. Now I also compute the tight Gabor window because I want to do Gabor multipliers, and I want to show you that this tight Gabor family. See, I didn't write it here. I'm using now the Gabor family. It's a Gabor family with respect to product lattice with A and B. And so somehow I have it in my workspace, but I should run this segment once more. So you will see a new low frequency signal, and then no, it's already in the next one. So I see that there was something missing here. Yeah, this last term is the Frobenius norm of my weight, and this is the deviation of the analysis with the tight window and synthesis. So it's really a tight window, because if you do analysis with this and synthesis with the same window, you get the identity matrix. So this is this test here. The next one was the plot of our weight function, and a representation of the signal in 3 different domains. Now, seems that, so kind of what you can see here is that I'm computing a Gabor. So what is the operator now? It's a Gabor multiplier. A Gabor multiplier is a multiplier which takes our tight Gabor window, takes the samples at A and B, multiplies them with the sampling values of our smooth functions at the lattice points, and it's not reasonable to take not smooth functions if you want to sample it, if you want to sample at different values. For example, if you want to study the influence of changing A and B a little bit each time you're computing a new GT, but you should use the same weight to see that the effect is really very similar or depending in a continuous way on your parameters. So a small change in your G will give a small change in the tight atoms. A small change in A and B has the same effect, and so on. Okay, so what is a Gabor multiplier? If you look at this as a matrix, it's a banded matrix, and you see here the labels are -20 to 20, so it's very much zoomed in. Why? Because I wanted to indicate that you see some weak side diagonals. So they're not very far away, but and it's from the effect of changing the effect of A. So it's not a strict diagonal matrix, but the main effect is a pointwise multiplication of the signal. Now, the same in this concrete setting, a little bit different, happens on the Fourier domain. So this is the Fourier representation. Now, in the spreading domain, I'm showing you again, always with the centered plot, the spreading domain, and you will say, oh yes, this looks like a very nicely concentrated thing. So the rectangle here on the right-hand side, right lower, the colored rectangle would be exactly the spreading representation of an underspread operator. But you see here some weak artifacts on the sides, and of course these things are relevant to give this here. Now here actually we should not zoom in so much, so maybe I should not zoom here anymore, but redo this picture. Yeah, maybe insert a break now and only redo this to show you how it looks in the original version without zoom. You will see it's a very thin diagonal-like matrix, hard to recognize that it's really not just a diagonal matrix. You're seeing this here, and you see this tiny spready function here. And of course, maybe I could do this centered plot for comparison of this time frequency weight. And what you would see is that the Kohn-Nirenberg symbol of the operator is very similar to the weight. So you see that there is a kind of lattice structure. And of course, I took a relatively coarse lattice to see this effect. If you would have a perfectly underspread operator, you would see a situation where this looks very similar. But here you only see, and I think it's a good example, that you have big coefficients at the areas where your weight was big. But this is in the Kohn-Nirenberg situation, and you should maybe also look at the coefficients. I don't show these coefficients to you here, and so on. So kind of the point is the computation of the Gabor multiplier, even the realization of this sybmol. It's a Gabor multiplier with the code of Maria Hampais, starting from the weight or so, is done with the help of the transition to compute the Kohn-Nirenberg or the spreading function of this operator, and then do this conversion. All these steps are using FFTs over and again. Now, I wanted to maybe to finish today with this part here. I wanted to show you how I'm creating, or how what we are doing with this BUPUs. So remember, BUPUs are bounded uniform partitions of unity, and you can get the triangular partition of unity by convolving it a rectangular function where the shifted boxcar functions are adding up to 1, and you smooth it by convolving it by itself. So the BUPU spline by itself is giving us the cubic polynomials, so convolutions of order 4. So the support is not just length A, but the length is 80. But we're doing it in a symmetric way, which is already a small challenge in the discrete setting, because if I'm allowing you to put 20 numbers in a symmetric form around 0, how can you do it? So our trick is to say, well, Either I make it not symmetric, which means I'm putting a value at 0, which is the first MATLAB coordinate. I'm putting 10 ones to the right and only 9 to the left. Or of course you can say, no, I put 9 values to the left and to the right. The remaining 1 unit I put in a symmetric way 1/2 and 1/2. That's what we are doing. Now it turned out that certain properties that the continuous B-splines have are not valid for the discrete setting in an exact way because of this mild modification. But we prefer to have BUPUs which have the property that the Fourier transform is also real valued. It should imitate the behavior of the sinc function. And so essentially what you should see here is this is a B-spline, which is a cubic polynomial in 3 pieces, but it arises as a convolution product of a boxcar function in a discrete setting. Now the Fourier transform is like sinc to the power 4, and you see it's so well decaying that it looks like a Gauss function. You could zoom in and you would see there are some minor side lobes, but it's harmless. Now, I was saying that in the description of the projection operators, and when we do the best approximation, we have to find that the projections are respaces. But these projections are respaces in the complicated space of Hilbert-Schmidt operators is the same as that the sigma of PL, which is the Kohn-Nirenberg symbol, is something which is, maybe I can, while I'm talking, insert this. So maybe I'm saying PGG is the G multiplied with RG. In our case, is this an n by n matrix or so? Sig PGG is mat2 Kohn-Nirenberg symbol of the PGG. And I wanted to show you this sig PGG while I'm talking. So this is actually, again, a bump-like function. So it is, you have it here now. Unfortunately, I didn't put a figure here. It is an, zoom in, zoom 5, 4. It is a function which is itself like a two-dimensional Gauss function. It has some phase factors, but they are not displayed. So this is what we have here. Now, how do you get the best approximation of such a family or so? Well, you're just looking at the bi-orthogonal system. The bi-orthogonal system is done by inverting a Gram matrix, and the Gram matrix is actually a cyclic matrix or so. I leave out this to you. The code TRL1 dual is just the code that is helping you to do this dual window, and I have also a BUP I for interpolating, so it's an interpolating spline. And once I have computed these 3 things, I'm plotting these in the order: the original BUPU, generator of my partition of unity, the dual element, and the interpolating element. So what I'm showing you here on the right-hand side is, this is a cubic spline. This is a Fourier transform, which is, as I said, sinc force power. But when you give me an element which is in the space, any signal, and you want to do a best approximation by the linear combination, you have to use this. You convolve your original function with this. You can also imagine, why is it having this shape? Well, it tries to be bi-orthogonal to the collection of shifts of this. So it should have a peak because you would like to have the scalar product of this guy with this guy should be 1. But if you shift this first guy to the right, to the left, it should be 0. That's why you have this negative effect. And so the bi-orthogonal element is very typically looking like this. On the Fourier transform side, you have such a picture. And you can say that this has to do with the situation where you try to do this with very narrow spaced Gauss function, then you get this dipping property. You have seen such things already for the dual Gabor window. You have similar effects of more and more oscillations on the side and an inverse dip in the center. And of course, you can try to do the interpolating thing, which is that you want to say a linear combination of cubic splines that you get by saying, well, maybe this, I mean, it's not 1 and not 0 here. So maybe I can take linear combinations of the left and right shifts, and this is possible. So you can do an interpolating element which consists of linear shifts along the lattice A equal 20. And then you take the Fourier transform. But we have already seen that, generally speaking, if something is interpolating like the sinc square function on the Fourier transform side, it will be a partition of unity like the triangular function here. So I'm just doing let's leave it out. The right-hand guy, the Fourier transform of the interpolating spline is this here. And it's plausible, but I don't want to visualize is that it's summing up to 1. So here we have the story that we take the Fourier transform of the interpolating spline, and we plot it, and we see it's a partition of unity. I think we should, maybe as a preview on one little thing that there are 1,000 things that I wanted to do, but one little thing that I will do next time in a bit more detail is the duality principle for Gabor atoms. And it's about the relationship between Gabor systems with lattice constants A and B, and the corresponding with the adjoint lattice, which is switching to the complementary lattice, but switch the order of B and A. So we have n over B, n over A here. And in short, you can look at this later on, it's the following situation. Whereas the Gabor family is generating the family, and you have a condition number of 194 for the Gabor frame operator, this other family is a family of only 2/3 of 480, so it's less element, but it's linear independent. So you have to look at the Gram matrix, and it's nice, it has the same condition number. And then you take the biorthogonal family, which is this one here, and it's generated up to a normalization factor by the dual window. So kind of, if somebody wants to expand all the signals of length n, he has to allow some redundancy. You're not able, or you're not allowed to use Balian, by Balian law, to use a basis of Gaborian type person. But if you want to transmit signals, then it's better that you make a lattice which is not sparse, but it's redundant, which is not too redundant, so it's having less points. And then the chances that you can, your receiver can obtain the information from the linear combination. Long ago, I was calling a theorem that I was deriving the piano reconstruction theorem. And the idea is to say, well, if my piece of music is well separated in time, so I'm playing one accord after the other, I know, and the musician is able to do it also, and my computer could do it in the same way, that the piano has separated frequencies. Now, of course, it's more complicated in practice, but let's assume it would be a program that's writing flute music. Then I would use the spectrogram to distill from the spectrogram and from the amplitudes of the spectrogram what the coefficients are that I need to synthesize the piece of music or so. So this is really kind of an important principle. So one of my former co-workers, Werner Kotzig, really went from our work on Gabor analysis here. He was the guy who was teaching me what the Kohn-Nirenberg symbol and the spreading function is and how it's related to underspread operators or so. And he went on and took a position where he was working with ADSL, with asynchron digital server lines at the time when all this popped up. So this is exactly where you want to upload and download and where you have to transmit information. Okay, I think we have used up our time, and therefore I'm thanking you for your patience.